Hello student, welcome back to one more session of analog and digital electronics. In this session, we will study about registers. So, first question is what is register? So, register is a group of flip-flops connected with a single clock. So, let me repeat, register consists of a group of flip-flops connected with this common clock input. Registers are commonly used to store the data, and also registers are used to transfer the data from one end to the other end of the register. That operation is called as shift registers. There are two types of shift registers, left shift registers and right shift registers. We will see that in later. In today's session, we will see a simple construction of registers. This diagram shows the construction of simple 4-bit registers. Here, we have connected 4 flip-flops. Since it is a 4-bit registers, 4D type of flip-flops are connected as shown in the diagram. So, these are the 4 flip-flops. Q0, Q1, Q2, Q3 are the output of the flip-flops. D0, D1, D2, D3 are the input of the flip-flops. All the flip-flops are connected with a asynchronous signal, that is clear. So here you can see the clear signal is connected to all the flip-flops. This signal is also called as asynchronous. Asynchronous means at any time output of the flip-flop can be set to 0. So asynchronous signals are connected. This clear signal, asynchronous signal is connected to all the flip-flops so that at any time the output of all the flip-flops can be made to 0. Other than that, clock signal is connected by means of AND gate. This is called as a gated clock. Here, when the load signal is high, then clock will be given to all the flip-flops, or all the flip-flops will be driven by the clock. When the load signal is 0, that is, when the load signal is 0, this AND gate will not work. This in turn disable the clock to the flip-flops, and flip-flop will remain in the last state only. When the load signal is high, the clock will be fed to all the flip-flops. Here you can see we are using negative edge triggered clock. That means during the negative edge of the clock pulse, the output of the flip-flop will change. As I discussed in my previous session, clock transition may be from 0 to 1, that is referred as a positive edge transition, or 1 to 0, that is referred as a negative edge transition. 1 to 0, that is referred as a negative edge transition. So, in the diagram, these flip-flops will change the state during the negative edge of the clock. So, example, if you take the input 1, 1, 0, 1, and initially by using asynchronous signal, we will make the output of the flip-flop is 0, 0, 0, 0. During the negative edge of the clock, this input is loaded into the flip-flop and moved to the output, and output becomes 1, 1, 0, 1. So this type of flip-flop also called as, this type of register also called as parallel in and parallel out register. That means whatever the input, so when the load signal is 1, this will enable the gate, and this will feed the clock to all the flip-flops simultaneously. So during the negative edge of the clock, whatever input present will be moved to the output. When load signal is 0, this gate will be disabled. This in turn block the clock signal to the flip-flops. So the output of the flip-flops remains in the last state only. So this is the construction of 4-bit register by using D flip-flops. Now we will see one more circuit diagram which makes use of enable signal. So the circuit diagram, this circuit diagram shows the 4-bit shift register by making use of a D type of flip-flops as explained earlier. The main comparison between this circuit and the previous circuit is, in the previous circuit is, in the previous circuit we are using gated clock because the clock is given to the flip-flops through by means of gate with the help of load signal. Now in this diagram, the load signal is directly connected to the chip enable pin of the flip-flops. This pin is called as chip enable or enable signal. When the load signal is high, this will enable the flip-flops. That time, whatever input present will move to the output during the negative edge transition of the clock. Whatever input present here, 1, 1, 0, 1, will move to the output. When load signal is 0, this will disable the flip-flops or this will disable the register and output will remain in the last state only. So in this diagram, student, you can see here, in this diagram, we have connected 4 numbers of flip-flops, D type of flip-flops with the negative edge triggered clock. You can see here negative edge triggered clock, and we have here a synchronous signal that is clear, that's also connected simultaneously. The main use of this asynchronous signal is to reset the output of the flip-flops to 0, 0, 0. When you make the clear signal high, the output of all the flip-flops becomes 0. So this is the logical symbol of 4-bit register. Here the D is represented in terms of bus. D can take value D0, D1, D2, D3, and Q can take value Q0, Q1, Q2, Q3. Similarly, we have a synchronous active low clear signal which is used to clear the flip-flops, and other than that we have chip enable signal also, which is used to, which will enable the particular chip or particular chip or IC. So this is the logical symbol of the 4-bit shift register. So this shows the transfer of data between the registers. In the diagram here you can see we are using 3 registers actually. This is the register A made of 2 flip-flops, register B made of 2 flip-flops, and we have one more register that is called output register, register Q. So we are going to transfer the data from register A or register B to the register Q by means of tri-state bus. That is, the output of the registers are connected to tri-state bus. So when the enable signal is 1, then output of this registers, output of this inverter becomes 0, which in turn disable this tri-state buffer, this and this buffer. Now on the other hand, this will enable this buffer and this buffer. So when the enable is 1 and load is 1, during the positive edge trigger of the clock, the data from this register, this flip-flop and this flip-flop, or from the data from this register A is moved to the register Q. That is, whatever data in this flip-flop here is moved to this one, and whatever data here is moved to this flip-flop, and it will be stored at the output Q1 and Q2. On the other hand, when enable is 0, let me erase this one. On the other hand, when enable is 0, that is, when this is 0, the output of the register, this becomes 1. So when enable is 0 and load is 1, the output of the register B, this is the register B, the output of the register B will be enabled onto the tri-state bus and it will be moved to the register Q. So when enable is 0 and load is 1, during the positive edge of the clock, output of the register B will be moved to the register Q. So in this way, data will be transferred from one register to the other register. This is one of the application in digital system, or a common operation. It is a common operation in a digital system. So now next we will move to the next diagram. In this diagram you can see here, so we have grouped 8 flip-flops, D types of flip-flops here. So those flip-flops are, the input to those flip-flops are Q, D1, D2, D3, D4, D5, D6, D7, D8. So 8 flip-flops are connected together, and output of these flip-flops are connected to tri-state buffer and tri-state buffer with the enable signal. All the flip-flops are connected with the driven by positive edge triggered clock as shown here. So when this enable signal is high, when this enable signal is high, let me consider like this. When the enable signal is high, this will enable all the tri-state buffers, and whatever the data appear at the input will move to the output of the flip-flops, or this tri-state buffer will move the data, output data, or it will allow the output data. When the enable is low, all the tri-state buffers are disabled and output of the flip-flops remains in the last state. So this is the 8-bit register, once again 8-bit register with tri-state output, and this is a logical diagram of the corresponding logical diagram of the corresponding 8-bit register. Now here we will see the data transfer using tri-state bus. Here we have 6 8-bit registers, that is register A, register B, register C, D, and register G and H. All these registers like register A, B, C, D is connected, the output of the registers are connected to the tri-state bus. Similarly, register G and register H, input of the register G and H is connected to the tri-state bus. Now, register A, B, C, D, one of the 4 registers are selected by means of decoder. We know the operation of the decoder. Decoder is based on the control signal E and F. So here, when the signal E and F is 0, 0, that will enable register A. When it is 0, 1, that will enable register B. When it is 1, 0, it will enable register C, and it is 1, 1, it will enable register D. Now, when the control signal EF is 0, 0, which will enable register A, and output of the register A is moved to the tri-state bus, and from here it will be passed to either register G or register H, depending on LDG, load G or load H is high. Whether load G is high, then the data will be moved to register G, or LDH is high, data will be moved to register H, or if both are high, then register will be moved to G or H simultaneously. In fact, at any time one of the signal will be high. So similarly, when EF is 0, 1, register B will be enabled and it will push the data to tri-state bus, and from there it will be moved to register G or register H depending on LDG or LDH. Whichever high, the data will be moved to the particular register. When EF is 10, that is decoded signal, control signal EF is 10, register C will be selected and it will move the data to the output registers. When EF is 11, register D will be selected and moves the data to the output register. So in this way, data will be transferred from the input to the output. It is a common operation in data transfer from between the register. So I have explained this one with the 2 to 3 scenarios. So now we will move to the next session. In the next session, you will see accumulator with the full adder. Accumulator with the full adder. Thank you. So, hello student, welcome back. Today we will discuss a n-bit parallel adder with accumulator. Actually, in computer circuits, it's frequently desirable to store one number in a group of flip-flops, which is called as accumulator, and add the second number which is stored in the register, leaving the result stored in the accumulator. So the one way to build a parallel adder with the accumulator is shown here. So this shows the full adder circuit is connected to the accumulator. So accumulator is a group of registers, group of flip-flops. Here we are using D flip-flop. So we have connected n flip-flops here. So D0, D1, like D0, D1, D high, Dn. Similarly, the output of the flip-flops as connected as an input to the full adder. So full adder will add two numbers, that is n bit of two numbers, x and y. Here you can see y contains n bit, y1, y2, y high, yn, similarly x. So all the flip-flops are driven by a clock signal, posteriorly triggered clock signal. Other than that, we have asynchronous clear signal which is connected to all the flip-flops in order to clear the output of the flip-flops asynchronously at any time. In order to add the two numbers, the number stored in the accumulator and the number stored in the full adder, we are using one more signal, that is add signal, that is connected to the chip enable pin of the flip-flop. So now, suppose that the number is x and y. So x is stored in the accumulator, then the number y is applied to the full adder input. And after the carry as propagated through the adders, the sum of x and y, appears at the adder output. And this is loaded into the accumulator on signal AD. That is, the signal AD is to load the output into the accumulator flip-flops on the rising edge of the clock signal. Before the addition can take place here, the accumulator must be loaded with some number. So initially we can load the accumulator with 0, 0, 0, 0, that is 0, 0, 0, 0. In order to make the output of the accumulator 0, 0, 0, 0, we are using here clear signal, asynchronous clear signal. By using asynchronous clear signal, you can make the output of the accumulator 0, 0, 0, 0. So output of the accumulator initially you can make 0, 0, 0, 0. So that 0, 0, 0 will be added with, that number will be added by the full adder with another number, and finally the result is stored in the accumulator on add signal enabled. So in this way, here n-bit parallel adder is constructed with the accumulator